Hello everyone, in this video we want to do an example of OMPT-D exam. So basically we want to do an integral involving trigonometric substitution method. So when you see such functions that have square roots in the denominator and basically no other terms in the denominator except for the dx, the differential of x, you should consider using trigonometric substitution. In this case that we have plus between the terms in the square root, we want to use, we actually can use hyperbolic sine and cosine of x. Actually one of them can be exploited, but we don't want to do that, and we just basically going to use just the tangent function, make it simple. So the first thing that we want to do is make this for a 1, due to the fact that if we differentiate the tangent of x function, we get 1 plus a 1 plus a tangent squared of x, or secant squared of x. So if we get this 4 out of the function, it becomes a 2 because there's a square root there, and it gets out of the integral. So we basically the integral of our function becomes, sorry for that, becomes such thing. If you get the 4 out, we should get something looking like this. So we want to calculate the integral of dx over square root of 3/4 x squared plus 1. So as I said, we want to do a substitution that involves tangent of a, say, equals to square root of 3/4 x squared. Now that becomes basically and simply this, and we want to differentiate both sides. So the differentiation of tangent of a induces, I'm just gonna write in the second form, dA equals to square root of 3/2 dx. Now if you look at the denominator, we have dx, and but the thing that we don't have is square root of 3/2 dx. So we are just gonna induce that on the denominator and induce its reverse outside the integral to produce a second square root of a dA. Now we'll see why is that so important to us. So we write the thing that we want to calculate was this, but I want to have this, but I don't have the square root of 3/2, so I'm gonna just add a reverse of it here, so everything will cancel out and I'm actually touching nothing. That's the beauty. So, and the denominator can stay the same. We are going to get to that in a few minutes. So, and that simply becomes 1/1, and now we're about to do the magic. So here we have square root of 3/2 dx. We found out that this term equals to secant squared of a dA. So we're going to put that in here. Don't forget the integral dA from now. Secant, of a dA, and in the denominator, note that we equaled we make it an equivalence. The square root of 3/4 of x squared is equal to tangent of a. Now, if we square the both sides, 3/4 of x squared equals to tangent squared of a, and that's what we have under this square root. So this one equals to tangent tangent squared of a plus 1. Okay, look at this. The denominator, we have 1 plus tangent squared of a. That's equals to secant squared of a. And we have a square root, so it becomes secant. So we have something that looks like this. Secant squared of a dA. And here we would have a secant of a. Well, look at that. That becomes, just gonna write it like this, the integral of secant of a dA, and there's a root of 3 here. Okay, that looks good. But the thing is that we still have an integral and it's based on a. We know that the integral of secant, if you don't remember it, the integral of equals to ln of all right. But the thing is that we don't want to calculate based on a. We want to calculate it based on x. So remember that we had equals to x. If you want to visualize that in a right rectangle, in a right triangle, excuse me, this, if this is a, look at the fact that the tangent of a equals to square root of x, 3 times x over 2. So this must look like this. So this side will become 4 plus 3x squared. Alright, hence the secant of a equals to 1 over cosine of a, which equals to 1 over 2 over, alright, let me write it like this.